You excited for electrodynamics? Not yet?
Okay.
Right.
That's
right.
I might get there with you, but
Right.
okay. Donald, you throw me off sitting over there, but I'll get used to it.
I can't see the word, sorry.
That's good, all right. I just have to, change is good. Have to adjust. All right. All right, gang. So, your assignment is due on Thursday. I'll have my usual office hours tomorrow at 1 o'clock. I'll be there on time, as opposed to last week. Sorry. Right. And we have an exam coming up a week from today. So the exam will be on electrostatics. That's lecture notes 1 through 6 and related material from textbooks of your choice. And the work that was done in the problem sets 1 through 3. Okay, I'll put the solutions up in a moment when I get back to my computer. So it'll be in class for the duration of the class, and it will be a closed book exam, okay? So no computers, no tablets, cell phones, smartwatches, and no notes. Everything will be provided for you. Okay. No need to calculate anything other than in your head with a piece of pen and paper. There will be no numbers to plug in anything. Okay. I'm happy to have a question review session. Maybe on Monday. I have a lot of flexibility. I'll send around. We could do it also at 5 o'clock when, I don't know if anyone, what would you prefer? I'll send around a message about that, but I'll have an hour long sort of question answer and yeah.
Will there be unseen problems?
Will be what?
Unseen problems, like problems outside the problem sets.
Well, we're not going to ask you the same problems that I asked you. They're going to be new problems. But they will be based on the concepts that everyone has learned in their homework and in class. Okay? But there won't be things outside the scope of what we have discussed in class and in homework in terms of the material. Does that answer your question?
Okay, sir. How many duration is going to be like hours for the exam?
How many questions?
Questions and duration.
Excuse me.
How many questions?
How many questions? The duration of the exam will be the duration of the lecture.
Which is 1 hour.
Yeah, around 50 minutes. So the number of questions will be, it's not, I haven't finished looking at the exam, so.
But we should be expecting nothing less than 4 questions, right?
No, it won't be. So let me be clear. The exam will not be like a problem set in the sense of, it won't be as long and as intense as one of your problem sets, okay?
Yeah, the reason why
It will be doable, and we will practice it and do it to see whether it's doable in the time constraints.
That means those problem sets.
Those problem sets are challenging, yeah, but then you have a week to do them, here you have an hour plus, yes? Oh, thank you. Yeah. It's not my new subject. All right. Very good. Get psyched, get psyched. All right. I'll put my war paint on. Woo! All right. Tranquility now. All right. Let's talk about the physics we're thinking about. Right. So let's just quickly review sort of the structure of things as we've had them at this point. So, you know, electrostatics sort of, in summary of what we sort of studied, is written here in a sort of formal way, right? We have the field equations that tell us what the divergence and curl of electric fields are at every point in space. And we have Gauss's law, which tells us about the local divergence of the field, or equivalently, what the flux of the field is through a closed surface in its relation to the charge enclosed in that surface, in the volume that is enclosed within that surface. And as we know, we can use Gauss's law to great effect when we have symmetry. It's the easiest way to solve the electric field. But that's kind of rare occasion where we actually can use Gauss's law, but when we can, we use it, okay? We also know that the field is so-called irrotational, meaning its curl, in electrostatics, the curl of the electric field is everywhere zero, which means the circulation integral, the line integral around the closed curve of the electric field is zero, okay? Yeah.
Is there an equivalent for method of images for magnetostatics?
Well, not in the current, we'll come to that a little bit later. When we start talking about macroscopic materials, there is a sense of that, but okay, let's just take one step at a time and let's logically, and then we'll get to it. So whatever pops into your head, let's not just interrupt, let's just continue, okay? Where was I? Oh yes, the circulation integral, okay? So the circulation integral of the electric field for electrostatics is zero, which is to say there's a conservative potential. And the electrostatic potential then tells us what the electric field is. The field is the gradient, and in its relation to potential energy, we have that minus sign. And thus, the potential satisfies Poisson's equation. And the solution to the Poisson equation is given here in terms of the Green's function with no other boundaries, okay? So that's, if we include all of space and all the charge, then that is the solution that we know. And moreover, of particular interest was the multipole expansion, where we looked at what the potential was far from the source, and we could do a Taylor series expansion. And the first non-vanishing term, if we have a net charge, is the monopole. It looks like a point charge at the origin. And then there are corrections. If it's if say it was a neutral, the first non-vanishing, a neutral distribution, the first non-vanishing term might be the dipole term. And the electric dipole moment is a vector that says something about the distribution of charges away from the origin, okay? Right, so we then started to talk about magnetostatics. Of course, I didn't say anything about the boundary value problems and so forth, the image charges, but we can talk more about that. This is sort of just the big picture, okay? In magnetostatics, the field equations are that the divergence of B is zero, which means there are no magnetic monopoles. There are no magnetic charges. The curl of the magnetic field is related to the local current density, which is the circulation integral of the magnetic field around the closed loop is related to the flux of the current density through the surface that is bounded by the curve, and that we call the enclosed current, okay? And again, like Gauss's law, Ampere's law is always true. It's not always useful, but when it's useful, man, it's useful, okay? Meaning that if we can have symmetry and we know the magnetic field is its dot product with the local tangent vector is the same number, we can factor it out and solve for the magnetic field just directly from Ampere's law, as you're doing in your homework, okay? And reminding yourself from days of yore when you solved such problems, which I'm sure you did. Now, the fact fact that the divergence of B is 0 means that the magnetic field itself is, well, no, this is not quite true, I didn't mean to say. What it means is that, because otherwise, the magnetic field itself is the curl of a vector potential. The curl of the vector potential is definitely physical. It's related to the magnetic field, and the magnetic field tells us something about the Lorentz force. But the divergence of A appears nowhere in physics. It doesn't actually affect anything. It's a figment of our imagination. We can choose it any way we like mathematically, okay? And so fixing what the divergence of A is known as choosing the gauge, okay? What I mean to say is that I can make a gauge transformation by shifting the I can shift the vector potential by the gradient of some scalar, what we call the gauge field, and that will in no way change B, because the curl of this is 0. It affects the divergence of A, but the divergence of A is meaningless. And so we can, by choosing this field, we can shift the divergence of A any way we like. And in magnetostatics, there's no other thing to choose except L equals 0, because why would you choose anything else? Just get rid of it. It's a nuisance, okay? And so from this equation, and together with Ampere's law, we have the field equation for A, which satisfies a wave equation-like thing, or a Poisson-like equation thing with a source. We choose this gauge, we get the Poisson equation again for each component, each Cartesian component of the vector potential satisfies the same equation as the scalar potential. And thus the solution is the same. So, because of the fact that this is a vector, and the vector direction might change as a function of position, which makes this a very complicated thing generally to solve. Like in one of your homework problems, where you have the rotating sphere. It's not so easy. Right, life isn't easy, oh God. All right, so, right, and again, what we did is we had a multipole expansion. And in the multipole expansion, where we look at distances that are much farther than any point in the source relative to the origin, then we had that this was equal to this, okay, when we did that expansion. And we showed that this is 0, so there were no, as expected, no monopole contribution. And the first possibly non-vanishing term looks like what we had over here, where this, I guess this is the minus sign. This thing over here is the magnetic dipole moment. Now, you know, in sort of Jackson and a lot of E&M texts, the magnetic dipole moment is called M. We often really call it mu, but mu is also the permeability, so that's one of the things that we're calling M. But just so you know, like in quantum mechanics, we always call the magnetic dipole moment mu, not M. and I always call the dipole moment D, not P, because P is momentum. But anyway, that's neither here nor there. Just mentioning that. Okay, now this object over here is a complicated mess, and what we had when we solved it is that we found that the magnetic dipole moment can actually be written as the following thing. It looks, in some sense, like the electric dipole moment, but with everything being a cross product. Okay. So that's the magnetic dipole moment vector for a localized current distribution, okay? And let me just see my notes here, what I wanted to say. Yeah. Right. So, and from that we get that the dipole magnetic vector potential is minus m crossed into the gradient of 1 over r. That contrasts or is analogous to what we have up here for the scalar vector potential for the dipole. Again, everywhere there was a dot product, now there's a cross product. And this, of course, is minus the gradient of 1 over r, is the electric field of a point charge. So this is equal to m crossed into r hat over r squared. Okay? Whereas for the scalar potential it was p dotted into that. All right. So that's where we were last time. Okay. Now there are a few, or maybe before I do that, what is the magnetic field associated with that vector potential? How would you find it? Given the vector potential, how do you find the magnetic field?
Curl it.
You take the curl it. Let's curl it. You actually do have curly hair for that curl, but you don't want to see it. Anyway, curl of A, which is equal to the curl of, let's see how, I'll write it this way, of this guy, because I put the minus sign out, the curl of M cross the gradient of 1 over R. Okay? It's the same thing as the other thing, it'll be evocative if I write it this way. Okay? So, let's see, how are we going to take that curl? Let's then look at the ith component of the dipole field. Okay? What is that? Well, that's the ith component of this cross product. And how do you write the ith component of a cross product? Exactly, you use the Levitchiv. So I have epsilon I j k, the jth component of this, and the kth component of this. But what's the kth component of this? Epsilon KLM, m sub L, the partial with respect to m, 1 over r. Everyone understand that? Okay, that's using our tensor notation to think about the components of the vector and components of the cross product. Now what? Now I have to sum over stuff. There's something fishy here. This should be J. That makes sense now. J, K. Yeah, that makes sense. Right, because this is the kth component of that. Right. Okay, now what do I do?
There's an identity relating the Levison's Vias to direct deltas.
Exactly. So I have a sum over K. And I remember, and I promise you don't need to remember this, I will. but I remember this, and maybe you do too, that this is equal to, I sum over these guys, this is delta IL, delta JM, that's carrying the remaining guys, minus delta IM, delta JL. Okay, so when I plug that in, so that tells me that the ith component of the dipole field is equal to minus delta IL, delta J, and minus I M, delta JL. And then I have a different M, that's the magnetic. In my notes I called it P because I was smart and didn't use M, because M meant the magnetic dipole. Yeah,
Did you accidentally put a double L?
I did. I accidentally did that. JL. Right. Okay, and then I have M sub L, delta J, delta M, 1 over R. Okay. And so what does that give me? Well, that gives me, I sum over this, I get minus I, M sub I, when I sum over that. The J, this becomes J, 1 over R, that's the first term. And then I get plus a M sub J, partial J, partial I, 1 over R. Okay? And the way I obtained that is I did the appropriate sum, and the way you do that is when you have a Kronecker delta, you can just replace one index by the other, because this is non-zero only when that index, okay? So this then is del squared 1 over R, and what's that? So we generally know that that's equal to a delta function, but I'm away from the charge distribution. So what is that? 0. R not equal to 0. Right? And so, given that, what I find is that the dipole is equal to M the partial respect to I M dot Bragg or equivalently, the magnetic field associated with this dipole is equal to minus the gradient of minus M dot. Now, why would I possibly write it this way? Because this magnetic field is exactly the same as the electric field associated with this scalar potential. If I were to take minus the gradient of this, that's the same field. So the field associated with the magnetic field associated with a magnetic dipole is the same as the electric field associated with an electric dipole. If they have the same vector, they give the same field. That's why we call it the dipole field. It's the same field, okay? Very good. So the the moral of the story is that the magnetic field of a magnetic dipole M is the same as the electric field of a electric dipole. Mhm.
Can you say the same things about the higher order?
Absolutely, absolutely. So all of the multipoles, the fields are the same. I can think about this, and this goes, Benny, to your question about image charges. I can think about this, and we'll come about this. This is like a pseudo scalar potential. There's a whole theory about this, and maybe we'll talk a little bit about it when we talk about materials. We know fundamentally the magnetic field is the curl of a vector potential. But in certain circumstances, when we're away from the charge distribution, the current distribution, it's equivalent to the gradient of a scalar potential, okay? And so all of the tricks of the trade that we know from electrostatics, we can apply in that. Very good. All right, so let's just maybe say a couple of words then now about two important cases. Okay, let's suppose I have what I call a planar current loop. So in a planar current loop, what I have is steady current flowing, I, and it's in some loop, and that loop is in a plane, okay? And I want to know what is the magnetic dipole moment vector associated with that current loop, okay? So let's just put the origin somewhere, doesn't really matter. There's some origin, and I have some DL over here. Oh boy, start again. Origin. DL. X prime. All right, let me explain what I'm drawing here. So what we know here is that the magnetic dipole moment is generally written as 1 over 2c, the integral d cubed x prime of x prime crossed into j at the position x prime. That's the current density. For a current loop, that is equal to, there's a constant current dl, x prime crossed into IDL. Okay, so and now I'm integrating over this contour, which is a closed loop, because I'm choosing that specific example. So here I just replaced d cubed xj by IDL. Okay? And now there's a little bit of geometry associated with this. This vector, first of all, in what direction does this cross product point? Out of the board, right? Because every point is perpendicular, so the cross product points in the direction of the normal to the surface, which in this case is n. And by geometry, 1/2 base times height is the area of that loop. So this is equal to dA. And so what we find in this problem is that this magnetic dipole vector, dA, is just equal to 1/2 base times height. It's that triangle, okay? So x crossed into dl is the dA that I've just drawn, that little triangle, the area of that triangle. And so m is equal to, for the case of a planar current loop, is equal to the current times the area enclosed by the loop. It's 1/2 base times height, is that. So there's no 2 there. The base times the height over 2 is the area. Yes, sir?
So M and B dipole are the same thing?
M is the magnetic dipole moment. It's M. B dipole is the magnetic field associated with that dipole vector. Okay? So, for example, we'll come back to it. Suppose I have a circular loop of current. What is the magnetic dipole moment associated with that if this thing has a radius r? And it's got current I going around in a loop. Pi r squared times this over c in this direction. Let's call it the z direction. Okay? So from that, I can ask, what is the magnetic field on the, say, any axis, but let's say on the z-axis, when z is much, much bigger than r? What's the lowest order approximation to this? Yeah, so this is going to be equal to minus, or I should just write the gradient of and that's going to be equal to, when you do that math out, now in the z direction. Is this the dependence that you expect for a dipole, that the field falls off like the cube of the distance? Yes, I see some good nodding heads. Correct. A monopole, the field falls off like 1 over the square of the distance. For a dipole, the field falls off. And if I were to sketch this magnetic field, what does it look like? Well, it looks like this. They don't cross like that. This is the magnetic lines of the magnetic field associated with the current loop. We should contrast that with the electric field associated with, say, this charge distribution. What does it look like? Similar, but not exactly the same. It looks like far away from the distribution, these fields are exactly the same to high approximation. When I'm right on top of it, where where the multipole expansion does not hold, the field of a current loop, the magnetic field of a current loop, is not the same thing as the electric field of 2 point charges. But far away from the distribution where the multipole expansion is a good approximation, they are, to excellent approximation, exactly the same thing. Yeah?
Earlier statement, magnetic field of a magnetic dipole, electric field of electric dipole being the same, does that only hold when the...
That's of the dipole part of the field.
Right, so does that only hold when the multipole expansion holds? Or-
That's correct.
Okay.
Well, this is just jargon. When I'm saying B dipole, this is of an ideal dipole, not a physical dipole. So it's,
That was
if
my
I,
second question,
yeah.
is that just a non-ideal case?
this field isn't not a pure dipole field. Far away, the dipole field dominates over the octopole component, etc. There's no quadrupole in this guy. Similar here, this guy is not an exact dipole. Far away, the dipole field dominates, but there is an octopole correction to it. When I say the dipole field, I mean an ideal dipole that has purely, the only thing in there is a pure dipole moment. That's a problem you'll see in problem 3 of your assignment. Yeah?
Is the pseudoscalar potential something unique to the dipole, or is there
No,
also,
it's for any, I could always do this.
for an arbitrary field or an arbitrary multipole?
For an arbitrary field,
Arbitrary.
yeah. I can always do it. But we don't use, I rarely use that stuff. I don't have a deep knowledge of it. Yeah. Okay, another example. Let's say I have a point charge moving with velocity v. Right. Let's say the point charge, let's say P, this is the velocity of that point. It also is at position x, say as a function of time. Okay. And I want to know what is, so this, for example, I have a point charge moving around in some orbit. Okay. And I want to know what is the magnetic dipole moment associated with this current. Because the charge is moving around, there's some current, and it's not necessarily in a plane. I do it as such, but it doesn't have to be. Let's also say the charge has some mass. So it has a charge Q and a mass M. All right. What is the magnetic dipole? We have that over there. The current density at some position x prime is equal to the charge density at x prime times the velocity. But the charge density is Q so that's the charge density given a charge at some point P. I only have charge density where I'm looking at x prime, and then times the velocity. So that's the current density. 1 second, I'll finish this and I'll answer your question. And now I can plug that in to the expression for the magnetic dipole moment. And I do the integral, and that gives me only non-zero where x prime is equal to where the charge is. Otherwise, there's no charge density. And so this then is equal to Q over 2C, the x of the particle crossed into its velocity. Yes?
You mentioned two important cases. Were those both in the top order, or is this the second?
This is the
important
second
case?
one.
Okay.
Uh-huh. Now, the position of the particle crossed into its velocity is something we know from mechanics. If we multiply this by the mass and divide by the mass, then this is the momentum. And the position crossed into the momentum is the angular momentum. So this is equal to Q over 2mc times the angular momentum of the particle. And so we learn an important thing, that the magnet, if I have a charged particle moving in an orbit, the magnetic dipole moment of that charge is just proportional to its angular momentum. And this constant, sometimes called gamma, is defined as the gyromagnetic ratio. Okay? And it's given by the charge to mass ratio in this case. Now you may have seen, or should have seen, I'm sure you have seen, in your modern physics and quantum mechanics, that when you think about an electron that has spin angular momentum, the magnetic dipole moment doesn't have this proportionality constant. There's a factor of two different. The G factor of the electron is, for spin, is 2. And that's a hint that the spin angular momentum is not coming from current. It's coming from some intrinsic angular momentum that is hocus pocus quantum mechanics, okay? But this is where that whole idea comes from, the notion of the gyromagnetic ratio. Very good. All right, let's just quickly do another example just to see how this multipole expansion stuff works. Ooh, that's not what I want. All of a sudden, let's see. Right. Sorry. All right, so, right. So let's think about a problem that's similar to what you're solving in homework. Where we have, let's say I have a disk. With surface charge, and it's rotating. So I have a disk. It's rotating with constant angular velocity omega around this axis. I'll call this the axis. Upon this disk, there is uniform surface charge density. And so it's a record player spinning around like this, and it's got surface charge density upon it. So there's current flowing, surface current. Okay. And that surface current is flowing in the azimuthal direction. And the amount of surface current is what? Of course, it depends on the radius that I'm looking away from the origin, okay? Because the speed depends on how far away. The guy's in the middle is sitting there, and this guy is spinning around faster, right? So what is the surface current density? Well, it's generally equal to the speed that this thing is moving times sigma, right? So it's omega r, and it's in the phi hat direction. Okay? All right, so that's the surface current density, and I want to calculate the magnetic dipole moment. Yeah,
Just for the point charge whipping around in a circle, there's two M's on the right-hand side of the board. Is the bottom M mass and the top one?
I multiplied top and bottom by n.
Okay, is that,
So because there was no, this, oh gosh, this is my, oh god, that's the mass.
Okay,
Yeah, mass of the particle, right? Yeah, and the mass of the particle, not the dipole moment. Lord. All right. Okay, back to our regularly programs here, all right? So, how am I gonna find the magnetic dipole moment vector in this case? Well, the easiest thing to do is to break this up into current loops and then add them up. So if I know what the magnetic dipole moment is of a given current loop, I can then just integrate and add them all up by the principle of superposition. So if I have a little dr here, then what this is equal to is pi r squared times the current at that, in that little di over here, over c. Okay. And what is the current di in this little loop?
Current density.
Dr, right? So di is equal to what?
Sigma omega
Sigma omega r, it's k at r dr, right? Because there's a little dr and there's surface flowing through the line. Remember that lexicon? There's a little bit of current flowing through that little dr.
Oh,
Right.
because K is current divided by distance.
Right, because the surface current is that, right? If I had volume current, I integrate over the area, surface current, I integrate over the line perpendicular to where the current is flowing. And so this is then equal to pi r squared dr times, or r cubed, sigma r over c. Okay? And so what I find in this case is that the magnetic dipole moment is equal to pi times sigma times the angular velocity r to the fourth over 4c, right? I just integrate this thing from 0 to r. And the integral of r cubed is r to the fourth over r. So this is the magnetic dipole moment then, okay?
Did you? Di equals that or K equals that? Because you're integrating over.
This is di, and I got di by multiplying k, oh no, there's no c there. Yeah. I multiplied k by,
Well, that was the last part.
okay, I'm sorry, let me get this clear. Di is equal to omega r dr.
Yes.
Dm is equal to the multiplying this by this dividing by c. And so I get pi sigma omega r cubed dr over c in the z hat direction.
Yes.
And now I integrate r cubed, and I get that. Thank you. Okay, so that's the magnetic dipole moment. So what do we think for this disk? What is the magnetic field on the z-axis when z is much, much bigger than the radius of the disk? Well, it's the field of the dipole, which is equal to 2m over z cubed, which is equal to pi sigma omega r to the fourth over 2 c z cubed in the z direction. Okay. That's approximately true. Now, if we solve this problem exactly, which we can, it's in the notes, which we did, because you may remember, I solved the problem of the magnetic field by integrating these little contributions from the Biot-Savart law, and we integrate each one of these from each current, and we add them up, and the exact solution we get is the following. So, I want to check that in the limit that I'm far away from this disk on the z-axis that I recover the dipole solution. How will I do that? I Taylor expanded. That's what you do, right? So you have, whenever you want to look at a limit, you do a Taylor expansion. And so what we have to do is firstly write things in terms of a small parameter, right? So we take this guy and I rewrite it. I factor out a z squared. I get r squared over z squared plus 2 divided by z r squared over z squared plus 1. This is 2 to the 1/2. Everyone saw what I did? I just factored out the z. And now what do I do? How do I do this Taylor series expansion? Binomial, yeah, don't be shy, I'm not shy. You do the binomial expansion. And what's the binomial expansion thing of this? So this is 1 plus something to the power this. So I rewrite this as approximately 1 minus a half, right? Because that's the Taylor series expansion. I'm so glad you can do that. And then we collect the terms and we subtract off things, and you'll see, ta-da, the notes, you get the lowest non-vanishing term is that. Okay? Know how to do that stuff. Okay, very good. So, far away indeed, this is a dipole. All right, lastly about this stuff, remember we talked about the idea of the energy stored in the charge distribution, and we were able to see that in a multipole expansion when we had an external field. So recall, in electrostatics, the potential energy stored in I want to look at the potential energy of a charge distribution in an external field. Okay, so let me just draw a picture here. I have some charge distribution. Okay, it's localized in some way. There's some origin, and there's some electric field it's not eternal, it's external. That's coming from some other source, like a capacitor plate, or some other charges sitting somewhere there. And I want to know what is the potential energy associated with this. That potential energy is I integrate over the distribution times the external potential coming from the external field. Okay? That's the charge times the voltage is the energy. And if this was localized around the distribution, then I can do a Taylor series expansion. So, plus dot, dot, dot. So, we had the quadrupolar energy, everybody's favorite Jackson problem, that where, the football, where we had the next term was the gradient of the field and the quadrupole tensor, et cetera, et cetera. So this is the energy that's associated with how much energy there is in the system when this charge distribution is sitting in an external electric field related to whatever the net charge is, and then the interaction of the dipole associated with that charge distribution with the external field, interaction with the quadrupole with the external field, etc. We want to think about the similar thing for magnetic fields, okay? It's a little more complicated because we don't have, what the heck is the potential energy? We haven't really talked about that associated with magnetic field. But we know about forces, okay? So let's now say I have an external magnetic field and there's current, okay? Now what I know is that there's going to be a Lorentz force on this current when there's an external magnetic field. The force on this current density due to this magnetic field is what? What's the Lorentz force? QB cross B, but that's for a point charge, and this is a current density, and so we got to integrate, and so this is the integral over the distribution J cross B. External. Okay, so that's the Lorentz force. So if I look at the ith component of that, I have 1 over C, I have epsilon ijk dq x prime j, the jth component of that, and the kth component of that. Okay. And again, I do a Taylor series expansion around the origin of the magnetic field. And so this is then equal to approximately, well, I'll just write it as equal to epsilon ijk, the 0th order term, which is just and then I have so what I've done in this expression is that I've expanded the magnetic field around the origin because this is a localized distribution and I'm only looking at things very close. In the situation where the magnetic field varies very little over the size of the distribution, and I made a 1st order Taylor series expansion.
Is the origin in an arbitrary place?
Oh, that it's got to be close to where the field. I mean, it's in an arbitrary place. However, it's in a place where the distribution is localized. If I put the origin too far from the distribution, then the Taylor series wouldn't hold. All right, what is this? Say. This is the integral of the current density over all space, which was the monopole, which is 0. Yeah. Okay. And this, let me just rewrite this as partial k. I'm sorry. X prime sub k partial k. I don't know why I have this twice. Lord, where's my mind? Let's rewrite this. J sub j x prime sub k partial k of the external k at the origin. That was exactly what we saw, and this was equal to the magnetic dipole moment that we saw before. When we, broke that up into symmetric and anisymmetric pieces and all of that stuff. So this thing over here is equal to epsilon j k l m sub l.
So isn't this limited because it's a Taylor series expansion to just that one point in space?
We always look at a Taylor series expansion around a point. However, it's a good approximation if the field itself is not changing very much over the size of the distribution. Okay? So that's where this holds in the same way that we had for the electric case, that we were looking at a charge distribution, and the dominant distribution, the dominant effect was related to, let's say, the electric field was right at the point. There's, of course, a correction term to that if the electric field is varying across that, but that contribution comes from the quadrupole. So we're always doing that kind of, yeah.
That looks like a lot of K's in that term.
Too many K's, yeah. Dummy. So we have epsilon I, J, K. Let's see, where did I go wrong? Yeah, there should just be a different index, because that was a dot product. Don't reuse your dummy indices, dummy Deutsch. Right? Yeah. Good. Sum over K, too many Ks. Thank you for pointing that out. Okay, so this object over here was related to, this is epsilon J L, I'll say P, M sub P. Once again, I'm not going to go, this algebra is tedious. We use the same thing I'm just erasing, where we use the identity that talks about how these things, when I sum over J, I get the delta functions. Question. If I want to do that sum, I want to use that identity. I've got to be careful about the cyclic order, right? Because I got to sum the first index with the last index. But this guy's in the middle. So I got to flip it and then put a minus sign in. Oh, God, got to keep track of all those things. Okay? So, very good. With that said, we get the following is true. That the force on that current distribution, localized current distribution due to the magnetic field that's external is equal to sum over K, MK, partial respect to I, dk, minus M sub I, partial respect to K, dk. All right? What is this?
Divergence of B,
That's the divergence of B, which is
0.
0. So, I finally get that the force is this depending on it, and can bring the gradient out. So this is equal to the gradient of M dot B. Sum over this, I can bring this on the other side, which is equal to minus the gradient which is a kind of potential energy. Because the force is minus the gradient of the potential energy. Yeah?
And all of our integrals up there, the B's are constant because we're evaluating them because of the Taylor expansion.
That's correct. That's why they come outside the integral. So what we see is that the potential energy of a magnetic dipole in an external B field is equivalent to the potential energy of a electric dipole in an external E field. I'm thinking about quantum mechanics. Right? And what that says is that if I have an external magnetic field and I have some magnetic dipole vector the lowest energy configuration is when the magnetic dipole is aligned with the magnetic field, okay? And the highest energy configuration is when it's anti-aligned. If there's some dissipation in the system, the system will tend to relax and tend to align with the magnetic field. Of course, if I don't have relaxation, what's going to happen to this magnetic dipole? Will it just go in this direction? In what direction will there be a force?
If there's no relaxation.
Meaning there's no dissipation, I just have this kind of potential energy. It will precess. This is the expression of a gyroscope. And the thing will tend to precess. It's called Larmor precession. Of the magnetic dipole around the direction of the magnetic field in the same way that an electric dipole will precess around electric field. This is a well-known phenomenon in spins of quantum mechanics as well. This is the electricity magnetism.
That's not the same thing as spin, right?
Exactly. So the spin angular momentum has a magnetic dipole associated with it, and the interaction of a magnetic spin with a magnetic field is exactly the same. And we know this is the Hamiltonian. That's why I put a hat on it, because I was thinking about that. A different hat. I wear hats, as you know, and it would precess. Yeah.
Is there a convenient way of getting intuition for the direction of the gradient of an optron?
No, so you'll have to think about the equation of motion in terms of what the torque will be. I'll let you think about that. The torque on this, given this force, is m cross v. So if I have the force, I can get the torque, and from the torque, I get that. Yeah.
So you wrote U sub electric dipole, U sub magnetic dipole. Is this just the dipole component of the?
That's correct.
Yeah, okay. So
It's just the dipole component of this general expression.
Okay.
Right. As we saw, there's a U associated with the, say, the electric quadrupole moment, right? And that electric quadrupole moment will depend not on just what the field is there, but its gradient, right? And that's the correction terms to this. Actually, I was interesting when I was visiting, wherever on Friday. We're talking about, this is something we're talking about in our group, about the latest developments in precision measurement. And you may know about clocks, atomic clocks, which are incredibly precise machines, and they work because you have energy levels of an atom that have a very well-defined frequency and a very long lifetime. And with modern lasers, you can lock your laser to this transition and use that to count the number of clicks. And that's how you count time, by these number of clicks. And now you have 19 digits of precision in this, okay? Now, more recently, it turns out that the nucleus of an atom has its own kind of shell structure. We usually don't study it in the same way we think about electrons filling shells of orbits. The neutrons and protons also have a kind of shell structure, and there are energy levels associated with exciting the nuclei. But those forces are strong forces, and those are usually mega electron volt things, and they're involved high X-rays or gamma rays. You're not going to lock your gamma ray laser to your nuclear. But it turns out that there is this one nucleus that people have found where there are two energy levels that are really close to one another on the scale of nuclear energies, and the energy difference between them is in the UV, okay? It's like 150 nanometer wavelength or something like that. So you can make UV light and so forth. Why am I telling you this? Well, the point is, and I just learned this, is that this excited state of the nucleus is slightly deformed compared to the ground state of the nucleus. So it has a slightly different quadrupole moment. And that slightly different quadrupole moment means that it's susceptible to a slightly different gradient of the electric field, and that would cause systematic errors. I mean, people want to look at this at, 21 digits of precision. You've got to think about every little physical detail like that. So your problem in homework is actually, I was just talking to someone, said, oh yeah, we got to calculate the gradient of the electric field, and the class said, well, I just gave that problem for homework. These guys are going to be so excited that what they're doing is more than just passing this stupid class. Anyway, yeah, someone had a question. Yeah.
Yeah, for our little precession diagram.
Yeah.
Should the dipole be precessing downwards? Around the
So-
forward axis? M cross B?
M cross B means that the curl is out, so it precesses that away. You're right. It goes this way around the thing. I'm gonna lose it. Absolutely. Yeah. All right. Yes, question.
Can you say the same thing for the potential energy of the dipole from other higher order poles?
The relation, they're all, it's true. It's always the
Can
same.
you generally say that because the fields were the same, so it would be the potential energy the same?
That's correct.
Is that obvious why that's true?
No, I think it's, again, this relationship that we can map what's going on for electrostatic fields and magnetic static fields to an effective pseudo-potential. So once I can map this whole story onto an effective scalar potential, then it's obvious. But without that, it's not.
Then will we do that?
No, I'm not gonna do that. We got more to do. All right, but we will conclude there, and we'll continue next time. Have a good rest of your day, everyone.